Okay, so beta sheet. Okay, so beta sheet. Uh, this can be beta sheet. This also can be parallel and anti-parallel. Okay, for example, if the beta sheet is like this, it is a pleated structure. Sorry, it is a pleated structure. So it is like this, and if it is like this, uh, it goes. That means what? That means this side is one helix. So this side is one uh, part of the beta helix. This side is one protein chain, and this side is another protein chain. Okay, and there is the bridge in between. There is the bridge in between by the hydrogen bond. This bridge is in between created by hydrogen bond. Okay. Now, if as per alpha helix, if it also goes to the same direction, then it is parallel. Then it is parallel beta helix or parallel beta sheet, parallel beta sheet. And if they run down opposite to each other, that means if one goes this direction and the other goes this direction, then it is the anti-parallel beta sheet. Okay, anti-parallel beta sheet. Fine. Now this is about the alpha helix beta sheet. Then we also discuss the Ramachandran name, the name of Ramachandran and his discovery about the phi and psi angles in protein chemistry. Now, in today, we will see the Ramachandran. We will see the Ramachandran plot, and then we will move to the actual homology modeling. We will see the Ramachandran plot, and we will then move to the actual homology modeling. Now, Ramachandran plot. To discuss the Ramachandran plot, we have to move here. To discuss the Ramachandran plot, we have to move here. First, here. Here we can see the plot. Okay, this is the plot. In this plot, two axes are drawn like this. In this plot, two axes are drawn like this. This is the x-axis, this is the y-axis. X-axis, it is the phi angle, and in y-axis, this is the psi angle. That means, according to the x-axis, we plot the dihedral and we plot the torsional angle, and along the y-axis, we plot the dihedral angle. Okay. Now, what does it? Here we see that different. There are 4 quadrants. In this quadrant, what is that? Here, there is. I am coming back to my drawing board to make the things. Now come to drawing board to make the things more understandable. Say you have the 4 quadrants like this. Okay. So here we have the phi. We have phi. Here we have psi. We have psi. So this direction is positive. So it is 0 degree. Sorry, this is 0 degree. This is 0. This is 90. This is minus 90. Okay. This is plus 90. This is minus 90. Okay. Similarly, this is psi. So this is 0. So this is plus 9. This is plus 90. This is minus 90. So in this, what these 4 quadrants means, if you have alpha helix or you have beta sheet or whatever you have, if you have right-handed alpha helix, if you have beta sheet parallel or you have beta sheet anti-parallel, in each case the phi and psi are restricted. That means there is a there will be a specific psi, there will be a specific phi, and with respect to the specific phi, there will be a specific psi. Okay, that means if somewhere the phi is 25 degree, then psi is restricted. That will say the psi will be say minus 37. Okay, say there will be minus 37, something like that. So depending, what does it mean? It means it is a specific phi psi restriction based on the kind of helix or kind of sheet you are choosing. Okay, so if it is right-handed alpha helix, then it has specific phi, then it has specific psi. If it is parallel beta sheet, it has specific phi, it has specific psi. If it is anti-parallel beta sheet, then it has also specific phi, it has specific psi. So in this four quadrant, where we have plus 90 to minus 90 variation, and we have here in the y-axis, we have plus and minus 90 variation. Everywhere you can, within these four quadrants, you can map any kind of phi and any kind of psi. Within these four quadrants, you can map any kind of phi and any kind of psi, because this convolutes total 360 degree of rotation. Total 360 degree of angle. The angle cannot exceed more than 360 degree in one rotation. So this convolutes your total 360 degree. Here 90, here 90, here 90, and 90, total 360 degree of rotation. So whatever torsional and dihedral angle may be for a particular alpha helix or beta sheet or something like that, we should be able to map that particular phi and psi in any of these quadrants. Okay. So Ramachandran, what he did, he mapped the phi and psi for all these kind of protein sheets and helixes individually. Ramachandran plotted all the phi's and psi's for each of these alpha helix and beta sheets and their parallel counterparts, anti-parallel counterparts separately on these quadrants. Okay. For example, here in the first quadrant, where both phi and psi positive, means where both torsional angle and dihedral angles are positive, he plotted that this is the zone, okay, where left-handed alpha helix will be there. Then what does it mean? That means if you have left-handed alpha helix, your phi and psi should remain within this zone. If you have left-handed alpha helix, then your phi and psi will remain within this zone. Your phi and psi may not be accurate. Your phi and psi may vary. It may not be very accurate. It may vary. But whether it varies also, it should remain within this zone. Okay. Similarly, he plotted that for beta sheet, if you have the beta sheet, okay, then your phi and psi will be plotted in this zone. If you have the beta sheet, then your phi and psi will be plotted in this zone. I am coming in this beta sheet, the parallel and anti-parallel beta sheets again have some segregation. Okay, the parallel and anti-parallel beta sheets have again some segregation, but overall the beta sheets, the phi and psi will be lying in this zone. In this zone, what is the mathematical characteristics? The phi is negative, but the psi is positive. The phi is negative, but the psi is positive. So if I have the coordinate of phi and psi here, so the first part will be negative, but the second part will be positive. Okay. Then I'm cleaning up this a bit. Then comes here this quadrant. This is the third quadrant. Here we have the right-handed alpha helix. Here we have the right-handed alpha helix here in this zone. Alpha R. That means if you have the right-handed alpha helix, your phi and psi will lie here. That means in this quadrant, both are negative. Both phi is negative and psi is negative. So if your dihedral angle and torsional angle both are negative, suppose you are modeling one protein and you are finding that for your protein structure, the phi angle and psi angle both are negative. That means what can you predict? Your protein is having mostly right-handed alpha helix. So this quadrant alpha right alpha helix has both negative. And interestingly, this quadrant usually has nothing. Actually, this because we have already got the alpha and beta sheets, alpha helix and beta sheet of this quadrant. Usually, no protein structure give phi and psi angles that are located in this quadrant. This quadrant means what? Where phi is positive, psi is negative. That means none of the protein structures usually available in nature where torsional angle is positive, but dihedral angle is negative. Okay. So this is a very important plot because yesterday I discussed the importance of phi and psi and their importances in the stability of the protein, because if they vary more than their permissible values, the protein bonds will break. So it has a greater importance in the stability of proteins. So this is a very important plot which you have to match once you have a protein structure. Whether you model a protein structure or whether you get a protein structure from PDB, just check once that your protein structure, if it complies the Ramachandran plot. Okay. So now again I'm going to some more details of Ramachandran plot. So I'm going to the screen again. Here now you have seen this is the left-handed alpha helix. The first quadrant I've already shown you. Okay. This is the second quadrant where I've shown you the beta sheet. In the third quadrant, I have shown you the right-handed alpha helix, alpha, and the fourth quadrant. Usually nothing overlaps. Okay. So now see in this diagram. See in this diagram. Actually, in this plot, actually I have taken plus 90 minus 90 because mathematically generally for an axis we take 90 to 90 because this angle is 90 degree. Mathematically this angle is 90 degree. So the variation is 90. So if we take this 90, we take this as 90. So I have taken 90 90. But in actual Ramachandran plot, it's better to take 180 180. Why? Because here each degree is taken for a 360 for each angle. Phi is a special type of angle, psi is a special type of angle. It is a separate angle, it is a separate angle. So Ramachandran has assumed that each angle can vary on its own over the rotation of 360 degrees. Each angle can vary on its own over the total rotation 360 degrees. So he has taken in positive direction 180, negative direction 180. So total is 360. Here also he has taken positive direction 180 to 5 and negative direction 180. So positive. So total is 360 because he has taken that the whole rotation for one angle can vary over 360. So here, if I go to the my whiteboard, now you can understand why it is 180. So now I can change this as 180. Okay? Mathematically we take 90 90 because this is the 90 angle, this is the 90 angle. Total is 180. But here, since each angle is separate here, not interrelated, so each angle can vary over a total rotation of 360. So I am doing minus 180 to 180 plus 180 to minus 1. Okay. Now we come here. Here. So now you see among these zone also we can have some more details. For example, this is the zone where beta sheet lies. Okay, this is the zone of beta sheet lies. Now what is the difference? One thing, what is the difference between this red and yellow zone? Red zone means it is the most probable zone. It is the most probable zone where the phi psi of beta sheet will lie. It is the most probable zone where phi psi of the beta sheet will lie. But it may vary. It is the most probable, but still it may vary. So how much it can vary? The YOLO zone give you the notion of how much it can vary. It is the most probable one, but it can vary up to this YOLO mark, up to this YOLO zone. That means there is a permission. Like in our assay, the best result is that we get 100% purity. Okay, but always we cannot get 100% purity because some error is there. The manual error, machine error, instrumental error, formulation error, excipients error, or drugs. There are some errors may be there. So we have some tolerance limit plus minus 10. That is from 90% to 110%. It may vary. Similarly, here we have the tolerance zone. That means in realistic cases, there may be some steric interaction, hydrophobic interaction, or some water molecule entrapment. Okay, so this may have some variation. So I have to give some tolerable zone, the permissible zone of variation. So this YOLO is the permissible zone of variation. Okay, this YOLO. But red is the most probable zone. Why it is YOLO here? Because left-handed alpha helix is very, I have already told in yesterday's lecture, the left-handed alpha helix is very scarce in nature. It is not usually found. So there is no red zone. It is already scarce. So there is no zone which is most probabilistic. So this is all the scattered zone. That means in this zone, if you find the left alpha helix phi psi, it's okay. Fine. Now you see the beta sheet, right? Alpha R here. Now also there is a YOLO zone here. That means some variation also seen in this zone. Although this zone is very thin. Thin means not much variation is allowed here. But still you may have some variation allowed here. That's why it's given YOLO zone. Now if I come here, now see in this beta sheet, the anti-parallel beta sheet will be in this zone. That means it is